This week's set of Bell problems is called Proofs Without Words. And in this geometry class, we have studied quite a lot of these theorems already. There are 7 theorems where the titles are given and the description is there. And there are 7 slides that you're going to interact with. Each diagram is interactive, which means we want you to play around with the sliders. So in screen number 1, we have an example of 2 intersecting lines. The first thing I want you to think about is, what does the diagram show? It shows 2 intersecting lines. Is there a triangle? No, I don't see a triangle. Is there a quadrilateral there? No, there's 2 intersecting lines. What happens when we move this? Oh, it's showing that if I move this, the angle that's formed between these 2 lines gets bigger. If I close it down, the angle gets smaller. Okay, what if I move this point? Oh, it's taking what was the angle and it's moving it down here, showing me that when I have a pair of intersecting lines, the angle that's formed that is opposite each other are going to be congruent. Which of these theorems then would make sense? So you're going to look through the list. You're not going to pick anything that says triangle, but I see vertical angles theorem. The angles formed by a pair of intersecting lines that are opposite each other are congruent. Okay, so I know that is correct for number 1. I'm not going to use vertical angles theorem for any of the other problems. I'll move on to number 2. What theorem does this interactive diagram illustrate? And I see that there's a triangle. I see that there are angles, pink, green, and blue, that are listed. I see that I can move this triangle and change it to a different shape. So it's not a right triangle necessarily. I don't want to pick Pythagorean theorem. It's not necessarily an isosceles triangle because it doesn't have to be isosceles. It could be scalene. So what happens when I move this slider? What happens to these 3 angles? Well, the pink and the blue are not changing size. They're repositioning next to the green. And I'm remembering that in a straight angle, it measures 180 degrees. So what does that mean? That must mean that no matter how I fix my triangle, no matter what it looks like, the sum of these 3 angles of it, the sum of the 3 interior angles of a triangle, right, is going to be 180 degrees. So you're going to find that theorem in the list. Don't use vertical angles theorem. You've already used that. Find that correct theorem and then move on to the next. I see another triangle, but this time I see the angles that are outside of the triangle. Notice I'm looking at my diagram before I'm looking at these words. And then I'm wondering, what about the triangle? Oh, it can be any size that I want it to be, any type that I want it to be. Okay, what's this dot and what's this slider? Well, let's look at these 3 angles and see what happens as I move the slider. What happens to these 3 exterior angles? They form a complete circle. How many degrees are there in a circle? And is that true no matter what type of triangle I start with? Yes. So what does this picture say, and what does it prove about the exterior angles of a triangle? Once you make your choice, you're not going to pick that choice again. Then you move on to a new shape and you say, oh, what's this? Is it a triangle? No, it isn't. It's a 4-sided figure. What do we call a 4-sided figure? You're going to think about that. You're going to realize that you might make this a square, you might make it a rectangle, or you might make it just any old 4-sided shape. Notice we're looking at the 4 interior angles. What happens when I move the slider? Okay, what is this showing you about the measure of all 4 interior angles? Well, this is 180, and this is another 180. Okay, this one here it takes you to another website called GeoGebra. And GeoGebra, when you go there, You're going to play around with a diagram. You're going to wonder what angle, what theorem is that GeoGebra going to prove? Then you move on and I say, oh, look at this. This is a triangle inside of a circle, a half circle. Does that matter? It does. It does matter because that forces my side lengths of my triangle to be exactly the radius of this circle. So no matter what the triangle looks like, these two sides, this side and this side, because their radii will always be congruent. If the circle has a radius of 5, that side is 5 and that side is 5. And that's 5. So I want you to know this is a special type of triangle where two of the sides are congruent. Okay, but what about this one angle? Is this one angle equal to anything else in the diagram? Okay, I think I see what's happening. Look over and see which one that is. And when you're done with this activity, you will know you are correct. All 7 screens are correct if you get the green check mark. All right, good luck and enjoy interacting with these diagrams. Try to figure out what is the diagram showing you and what is it saying about the math.